Hi, my name is Kyle Franklin, and I'm a senior solution consultant with Lucas Systems. You may know Lucas is the people behind Jennifer, which is voice-enabled picking. But now she acts as the brain of our DCs, orchestrating work around the warehouse. In this demo, we're going to show you Lucas Dynamic Work Optimization, aka DWO, which is an absolute game changer for warehouses. We'll show you how it can be used to optimize the work of people using carts, pallet jacks, or other riding equipment, and how it can be used to orchestrate and optimize robots alongside human workers. This means less travel, fewer people, and fewer robots. We're going to spend the bulk of this discussion discussing the how and the what, but let's first ask the question why. As you may be aware, warehouse labor is becoming more and more scarce and expensive. In a DC, the highest ongoing costs are typically in labor. Among all the activities in a DC, the biggest chunk of labor is typically spent in order picking. Within picking, for most DCs, the largest chunk is wasted in travel. Users walking from location to location in a warehouse. On average, order pickers walk between 5 and 15 miles during a shift. DWO directly attacks this travel challenge. We see significant reductions in labor hours, both in picking and admin times, as well as increased throughput, all without physical infrastructure or WMS changes. This is software you can have in your warehouse in a few short months. It's not waiting in line for a conveyor that's on back order for the next 2 years or a multi-million-dollar automated pick tower. Another great thing about the solution is that it's proven. We've combined sophisticated data science with decades of deep warehouse expertise to create this product. It's not a theoretical MVP in search of a beta. It's currently installed and running in production in over 25 DCs across 9 countries in North America, EMEA, and the Asia Pacific. So we don't make software for conference room demos. You're not going to see a lot of 3D animation here. It's not going to look like Avatar. We make software for DC workers and leaders. These are some actual customers that leverage this specific software module in production. Johnson & Johnson, CVS, British Telecom, and others. Some of the largest companies in the world have turned to DWO to solve their warehouse challenges. And in that time since the first install, we've been able to iterate and improve on it based on real-world learnings for future DC workers and customers. So now that we've discussed why, let's look at how we do it. It consists of 3 main components: dynamic prioritization, which is deciding which orders to work on, path optimization, calculating the most efficient way to pick an order, and intelligent batching, which blends those two to determine the most efficient set of orders to pick in one trip to reduce total warehouse travel. First, we'll look at prioritization. Before we can get into creating efficient work, we have to respect that warehouses have priorities, be it certain types of orders, service levels, or carrier cutoff times. And these priorities often shift rapidly throughout the day. To handle this, we group orders into priority groups. Then they are automatically slotted and prioritized appropriately. Because we operate on demand, when a user asks for work, they always get an optimally prioritized batch of work, even if a coordinator rushed out an order just seconds before. Once we have these orders grouped into codes, we allow users to set and configure priority settings on the fly or by using the shown batch scheduler. You can choose how far down the list of orders you want to include in batches and how to treat those orders instantaneously. It lets you easily adjust the balance of priority and efficiency. So now that we know what orders are available to pick, let's look at how we can pick each one faster. Consider the following warehouse map and visual pick list. The blue dots are individual picks for a single order, all of which need to be picked by our RF picker here at the start. Now we see their pick path dictated by a standard serpentine warehouse sequence. The user will traverse each aisle that has picks in it, and in most cases traveling the entire length of the aisle to pick them. In this example, they would have traveled about 934 feet. Let's look at the path generated by our pick path optimization engine. It uses a number of traveling salesman mathematical algorithms sourced by our team of data scientists. It evaluates travel costs over a digital map of the warehouse. Now we see we have significantly reduced travel time for our picker by resequencing these picks. Instead of picking those items at the bottom of our map in aisle sequence, we save a ton of walking by grabbing those at the very end. This results in an estimated savings of 18% for this order. All of this extra travel is eliminated. Now the key is Many of us have seen really sharp pickers in action, ones that can find workarounds or shortcuts that shorten this distance. But what about your newer pickers or your temporary agency workers you just brought in? Our engine helps to democratize these shortcuts, in addition to making our fastest pickers even better. So now that we can use math to help us build efficient routes, and we know which orders can be picked based on priority, let's look at the third component, intelligent batching. One of the key ways that warehouses can save on travel time is by batch picking orders. We now see a group of the next available orders in the system overlaid on our map. We now see the pick path generated by our engine to pick order number 1, the highest priority order in the system, traveling a distance of 432 feet. Most warehouses batch in a first in, first out manner, so the user will be assigned order number 2 to pick with order number 1 in their batch. Picking both together results in a total travel of 704 feet, much shorter than if they had picked them separately. However, there is a better way. Lucas's AI-based tool looks at the pick paths of all of the orders we determine were eligible to help determine what the optimal batch is. Looking at the map, which order matches really well with our current pick path? If you noticed, order number 6 in green almost matches our path perfectly and will make a great addition to our batch. We only see a small amount of additional travel is needed to complete both orders, resulting in 456 feet to pick both orders. Consider how much greater the benefits would be once we pick batches of 4, 8, or 20 orders, as many of our customers do. Also consider that these benefits can be leveraged not only for humans, but for robots as well. So we'll now take a look at a quick example of the DWO engine coordinating these picks between these humans and robots. One of the key differentiators is that we're able to give instruction to the AMR and the human because they have a device of their own. This differs from the more common model of having humans visually have to look around for their closest robot. As you see here, the picker is directed to the pick in the next aisle instead of the robot that they can see in the current aisle. And another picker has been directed to this zone because there's enough demand. Now the robots are repositioned along with the humans in concert. Picker 1 and 2 continue to get instructions and complete their picks. Because they are directed, they don't have to wait for a robot to know what to do next or scan into each robot before they pick. They can confirm placing items to the correct robot or tote by speaking a check string, scanning, or using RFID. To summarize, this slide shows the path traveled by Picker 1 with only robot-assisted picking. The total travel distance is about 412 feet. This slide shows the path with human-coordinated robot picking, showing travel of 202 feet, over a 50% reduction in human travel. Now with the paths overlaid, you can see the total delta. We've reduced travel for both the humans and robots. Less travel equals more productivity, and thus fewer needed human hours and fewer robots as well, lowering those high RAS fees. Now that we've seen how DWO can help reduce travel for humans and robots and orchestrate the DC, let's talk impact. Through this product, we expect to see an average of 40 to 70% reduction in total travel. We've seen numerous customers reduce needed labor in these areas with DWO by over 50%, with one customer improving productivity by 122% in a couple months post-go live. Lastly, these results come quick. A typical project from design to go live is about 3 to 4 months, including training, so we can get to an ROI very quickly. These are real numbers from real customers like Johnson & Johnson, Southwire, and British Telecom. Thanks for joining us for this presentation, and please feel free to reach out if you have any questions.